Right, we're looking at trig graphs. Now, on a unit circle, we know that with an angle like this, the height is the sine valley. So we can sort of imagine sweeping this angle around, right? So the angle starts off quite low. So if we look at an angle and whatever the sine value is, it's actually going to start off with no height at all. As that angle gradually increases around, eventually you reach the top height when the angle is pi over 2 or 90 degrees at a height of 1. So that's going to look like this. And then the y value, or sine of pi over 2, equals 1. Eventually we're going to sweep around even further, right? So you're going to go all the way around to pi, and then the height will be 0 again. So we're going to get, at pi, a height of 0. When we look at 3 pi over 2, or in other words 270 degrees, we're actually sweeping all the way around, so the sine values have gone negative, and that goes down all the way -1. When we got 2 pi, we're back to the start, and it actually just keeps rotating around the circle. So for bigger and bigger angles, that's what it looks like. It just keeps going around in that same pattern. We can see it here really nicely on this little diagram. The green line is sine, and you can see a graph of it. So over here, if theta is 180 degrees or pi, you get back to nothing, and it eventually drops down and then goes up again and keeps looping around. So trig is actually about circles, but it's also about waves. These model a lot of things in nature, temperatures, actual waves, music, light, all that good stuff. We're just going to talk about the graphs in theory today. So that's what it looks like. And we do various translations to it. So that's the full selection of translations we do. The A value changes the stretch. B will sort of squish and stretch it around, like squish it horizontally. C will move it horizontally, and D will move it up and down. Now, if we look on Desmos, normally C and D are 0 on a sine graph, and A and B are 1. That's sort of the starting point. And we can see that A will change how much it stretches up and down. B will sort of squish it in and out, like a bit like a slinky or something. C will move it left and right, the whole thing, and D will move it up and down. And then we can sort of figure out what graphs are from a picture. So we've got this graph here. It's got pretty much the standard sine shape. So we just got to figure out what A, B, C, and D are. Doesn't look like it's being moved left or right at all, because it still starts at the very start like a normal sine graph. I might just put a normal sine of x here so we can use that as a reference point. There it is. So it still starts normally, so C would be 0. It doesn't move up and down at all. It looks like it's still repeating every 2 pi, so it's not any squishier. By the way, we call this distance here the period, so how long it takes before it repeats itself. That's 2 pi. And by the way, you can pick any 2 points that are the same, so the 2 maximums, for example, so that distance there is 2 pi. Just be sure that if you're picking 2 points in the center like this, you don't just pick the distance to the next center point, you pick the distance until it repeats, and it won't repeat until it's coming back up through the center. So that's why the period is 2 pi. So anyway, the period is still 2 pi on this graph, so B would be 0. There's been no horizontal squishing or stretching. The A value was 2. B would be 1 because we haven't messed with B. A is 2. So what this is going to be is y is 2 sine of x. And if we look on Desmos, we can actually graph this. You can see that sine of x versus 2 sine of x, it's the same, it's just stretched up a little bit. Okay, next graph we got to look at. So we've sort of got this line here at y is 3, that's where it's centered. So if we try and figure out what all the letters are, D would be 3. We haven't moved it left and right at all. it seems to still be repeating every 2 pi, so we haven't stretched it. B would stay as 1, and A would stay as 1 as well, because this goes up by 1 from the center point, and then it also goes down by 1, so we haven't vertically stretched it at all. So this graph here looks like y is just normal sine of x, no modifications in there, plus 3 on the end. Now if we try that, then we should see, yes it is, it's moved up by 3. Here we go. So it looks to me like the period is now pi. So this only goes pi before it repeats. And if you want to double check that, pi over 4 up to 5 pi over 4, if you subtract those two numbers, that's a length of pi. So the period equals pi. And I've also given you a handy formula to know what the period is. 2 pi over b. So, well, b is 2 pi over the period. So b is going to be 2 pi over pi. So it's 2. So if you know what the period is, you can just use that formula to work out what your b value should be. Okay. Now, A, C, and D haven't changed at all on this graph. It's still sort of all normal. So A is 1, B is 2, C is 0, D is 0. A and B are usually 1, C and D are usually 0. So if I look at a graph sine of x versus sine of 2x, I can see that it is just sort of squished in and it repeats twice as quickly. Okay. This wave is much higher pitched than a normal sine wave. All right, this one here, we've got a little bit of movement. So it appears that the period, so 2 up to 5.14, that's a gap of 3.14. So the period is pi. The period should normally be 2 pi, so b's being messed with. So b is going to be 2 pi over pi, which again is 2. And also this graph starts at 2. So it's supposed to start on a sine graph starting from the origin and going up. This one does that, but it starts from 2 rather than where it should start, which is over at the origin. So that would tell me that the C value is 2 and everything else is left unchanged. So y has got to be sine of 2 brackets x take 2. And if we can do that, that should give me the graph that I'm after, 2 and 5.14. So there's been 2 different things happening with this. And if we wanted to like move it up or something, you absolutely could as well. Okay, this one here, there's 2 ways you can go about this. So it's like a normal sine graph, but it's been flipped upside down. So you can just make a minus 1. And if you do that, it should work. So minus sine of x. It's a flipped upside down version of the original sine graph. By the way, that might be how noise cancelling headphones work. And you could also think of it as you're only starting at pi. So it's normal sine of x, but the C value is pi and everything else is normal. So, or see that green graph and the blue graph, they describe the same thing. How about that? So there are 2 correct answers here. In fact, there are infinitely many correct answers, but those are the 2 most common ones. This one here, it's got a combination of, I think, everything. So A, B, C, and D, and we'll go through the whole process. D is the center point, it's the easiest one to find. That is 10. A is the length from the center point up, so that's 5 up and 5 down. If you want, A can also be the total height divided by 2, so the total height is 10 and you can half that, but A is 5. For B, the period is, let's see how long it takes to repeat, so 0 up to 24, so the period is 24. B has got to be 2 pi over the period, 2 pi over 24. And C is where it sort of starts, or where it should start going up. So that number there is 18. So C should be 18. So what I'm expecting is 5 sine 2 pi over 24, or maybe I'll just simplify that to pi over 12. X take 18 plus 10. That's how we do that graph there. Now let's see how it works. So just jump onto Desmos again. We had 5 sine pi over 12, x take 18 plus 10. And that graph up there does sort of match what we need. So that's really good. By the way, we didn't talk about cos graphs, but cos graphs always start at the top, whereas sine graphs always start at this bit that's sort of in the middle going up. So one other way that you could do this is you could have this in as a cos graph, and then you wouldn't need this take 18 bit, and that would also fit. Same thing.